In the early 20th century, Albert Einstein, a brilliant physicist, revolutionized our understanding of the universe with his groundbreaking theory of relativity. This theory, divided into two parts, special relativity and general relativity, transformed our perception of space, time, and gravity. Special relativity, published in 1905, deals with the relationship between space and time for objects moving at constant speeds. General relativity, published in 1915, extends these ideas to include acceleration and gravity. Before Einstein, physicists believed in a static and absolute universe, as described by Isaac Newton's laws of motion and gravity. Time was considered absolute, meaning it ticked at the same rate for everyone, regardless of their motion. Space was also considered absolute, meaning it remained the same for all observers. However, Einstein challenged these long-held beliefs, proposing a dynamic and interconnected universe where space and time are not separate entities but rather interwoven into a four-dimensional fabric known as space-time. In this new reality, the speed of light, approximately 299,792,458 meters per second, plays a crucial role. Einstein postulated that the speed of light in a vacuum is constant for all observers, regardless of their relative motion. This groundbreaking idea forms the foundation of special relativity and leads to some astounding consequences that challenge our everyday intuition. Special relativity is founded on two fundamental postulates. The first postulate states that the laws of physics are the same for all observers in uniform motion. This means that whether you are standing still, walking down the street, or traveling in a spaceship at a constant velocity, the fundamental laws governing the universe remain consistent. The second postulate of special relativity is even more profound. The speed of light in a vacuum is the same for all observers, regardless of their relative motion. This might seem counterintuitive at first. Imagine chasing a beam of light while traveling at half the speed of light. You might expect the light to appear to move away from you at half its usual speed. However, according to Einstein, the light would still travel away from you at the full speed of light. This seemingly paradoxical idea arises from the fact that space and time are not absolute but relative. To accommodate the constant speed of light, time and space must stretch or contract depending on the observer's relative motion. This is where the mind-bending concepts of time dilation and length contraction come into play. One of the most intriguing consequences of special relativity is time dilation. This phenomenon describes how time is not absolute, but rather stretches or slows down for objects in motion, relative to a stationary observer. The faster an object moves, the slower time passes for it compared to a stationary observer. Imagine a clock traveling at a significant fraction of the speed of light. From the perspective of a stationary observer, the moving clock would tick slower than an identical clock at rest. This effect is not due to any mechanical malfunction of the clock, but rather a fundamental property of time itself. Another fascinating consequence of special relativity is length contraction. This phenomenon describes how the length of an object moving at a significant fraction of the speed of light appears to contract in the direction of motion from the perspective of a stationary observer. The faster the object moves, the shorter it appears. Consider a spaceship traveling at a high speed relative to Earth. From the perspective of an observer on Earth, the spaceship would appear shorter in the direction of motion than it would if it were at rest. This effect is not an optical illusion, but a real consequence of the interconnectedness of space and time. Perhaps the most famous equation in all of physics, MC2, also emerges from Einstein's special relativity. This elegant equation reveals the profound connection between mass and energy, demonstrating that they are not distinct entities but rather interchangeable forms of the same fundamental quantity. The constant c, representing the speed of light in a vacuum, emphasizes the immense amount of energy stored within even tiny amounts of matter. This groundbreaking equation has had profound implications for our understanding of the universe and has led to revolutionary technologies. It explains the energy source of stars, which convert a small fraction of their mass into enormous amounts of energy through nuclear fusion. It also underpins the development of nuclear power, where a small amount of mass is converted into a tremendous amount of energy. The mass-energy equivalence principle fundamentally altered our understanding of the universe, revealing the hidden energy within matter itself. This realization continues to shape our exploration of the cosmos and our quest to harness the power within the atom.
Like and subscribe to start your journey today.